the general form of the steady state solution then, whether we're talking about voltage or current, is going to look like this. It is amplitude, cosine, omega t plus some phase angle. The phase angles here are different. The amplitudes are going to be different, but the thing that's going to be the same are the two omegas here. Okay. Now we're going to use something that's going to aid us in this. So we're going to rely upon something that is called a phasor. And a phasor is something that carries amplitude and phase angle information. So it carries two bits of information, the amplitude and the phase angle. And remember, for solving the types of problems that we're going to be doing in here, we need to know the amplitude and we need to know the phase angle because we know the general form of the solution. Okay, now the amplitude and the phase angle involve this phasor, and the phasor is an aid to help us do something. What the phasor does is it takes something in the time domain. Now what do I mean by the time domain? I mean I've got some t's in it, like omega t. This would be a function that's in the time domain. And it transforms it into the frequency domain. So what the phasor does is it goes from the time domain into the frequency domain. So here's the general flow of what's going to happen here. We're going to look at circuits, and those circuits, in fact, everything we've done up to this point is in the time domain. We're going to use phasors to transform those circuits into the frequency domain. Now, once they're in the frequency domain, you're going to discover that everything that we have done so far in this class applies. So all the techniques, node voltage method, mesh current method, superposition, KVL, KCL, all of those things that we've talked about apply over here in the frequency domain. So you find your solution over here in the frequency domain, and then after you found your solution, then you transform back into the time domain and you write your final answer. Once again, time domain is where we start. We use phasor transforms to go to the frequency domain. We do all of our analysis over here that we need to, and then we go back to the time domain. Okay, so now that you've got that, what you need to know is how to do a phasor transform. So the phasor transform is going to transform a function from the time domain into the frequency domain. Okay, well let's see how to do that. So let's say that we've got this voltage function right here. And what we want to do is we want to transform that. Well, typically the way that you would write this, mathematically speaking, is you would say P is the phasor transform. And we take V is this function right here. We take that function into the phasor transform. And then what we get out is the phasor of that function. Now, in your textbook, the phasors are illustrated as kind of like vectors. They have bold print. But when we're on paper here, we need a way to illustrate that's bold. So we're going to do it the same way that we do it on paper for vectors. And in many ways, these are kind of like vectors. We're just going to put an arrow over it. So that indicates phasor V. So we've transformed this into that. Okay, so the phasor then of V is, we're feeding into this phasor transform V sub m cosine omega t plus phi sub V, and we're getting out of that a function that is in the frequency domain. So because what's on the left-hand side here is in the time domain, what's on the right-hand side is going to be in the frequency domain. Now, there's a lot of different ways to write this. It comes about this way. V sub m times e to the j theta. This is the amplitude. So that's the amplitude. This, and I noticed the notation change here. That was a mistake on my part. This should be phi sub v. This is the phase angle. Okay? So what we've done here, I don't want you to overcomplicate this because this is really, really simple. What we've done here is we've taken this time domain function and we've transported it into the frequency domain, but when we did that, the amplitude and the phase angle is really all we need. That's all we're interested in. So let me show you an easy way to do this. Let's say that I have this function right here, v sub m cosine omega t plus phi sub v, and I want to plug it into the Phasor transform. What I should get out of it is this. And remember I said there's a lot of different ways to write this. One of the easiest ways to write it is in polar format. Remember, you probably learned polar coordinate system somewhere in your algebra career. Well, you've got polar and you've got rectangular. Polar coordinates, you have some radius and some angle. Whereas rectangular, you're talking about a point in space that has x and y coordinates. Well, polar and rectangular, you can convert between those two coordinate systems. But when I'm doing this Phasor transform, it's real easy just to write down in polar format, because polar is the amplitude and the phase angle. So when I do this, I'm going to write it down this way. V sub m, where did that come from? That's the magnitude. That's the amplitude. Angle phi sub v. Now, remember I said this is a lot easier than what you might first think. It is trivial. To go from this to that, you just write down the amplitude and the phase angle. And that's really it. We have just transformed this time domain function into the frequency domain. We've gotten rid of the time. Let me do that one more time. Maybe it was so easy that you missed it there. So let's say that we've got a real function v equals 72 cosine of 377t plus 23 degrees volts. Okay. I want to find the phasor of that. In other words, I want to find v phasor. It's just equal to 72 angle 23 degrees. And that's it. So I have transformed from the time domain into the frequency domain. The units would still be volts. And that's it. You've just done a transformation. Now when we did this, this is in polar coordinates. And polar coordinates in general has r and some angle. Remember, polar coordinates, to represent that point, I can represent it as an r and some angle. But that could also be expressed in rectangular coordinates as x and y, where this is the x-axis, that's the y-axis, like that. So if I wanted to express this right here in xy coordinates, I would have to do a transformation from polar to rectangular coordinate system. So in rectangular, if you want to do the transformation, the x is equal to r times the cosine of the angle. The y is equal to r times the sine of the angle. So these are used for transformation from polar to rectangular. So if I take my r, 72, times the cosine of 23 degrees, then that gives me 66.28. This is the x value for that. The y value for that would be 72 times the sine of 23 degrees, and that turns out to be 28.13. So V, phasor V, could be written as 72 angle 23 degrees, but it could also be written this way. 66.28, that's the x component, plus the y component is 28.13. Now, to separate the x and the y component, we still want to write all of this as one quantity, as one equation. So here's the way it's usually done. Plus j. So you add that plus j in between. So this becomes the real portion of a complex number. This becomes the imaginary portion of the complex number. So if I wanted to go from polar to rectangular, you need to be able to do that. Here's the equations to go from polar to rectangular. In other words, to go from r and theta into x and y. Now, if you want to go the other direction, let's say you want to start with x and y and get r and theta, well, you know how to do that. R is equal to the square root of x squared plus y squared, and then theta is equal to the inverse tangent of y over x, like that. And you think about it here on your coordinate system. Let's say there's our point there. This is r. Then you imagine a triangle. This is the x portion. This is the y portion for our point that's up here. And this is the angle theta. So r is just the hypotenuse of this rectangle, x squared plus y squared. And theta is just the tangent, or tangent of theta is just y over x, opposite over adjacent, like that. As long as you can keep that straight, then this is the conversion from rectangular to polar. This is the conversion from polar to rectangular. Now, having said that and having shown that, I guarantee you that somewhere on your calculator, these conversions are built in. You need to know how to do those. And I would recommend you spend a few minutes with your calculator trying to convert between polar and rectangular to polar. And the reason for that is because that's going to be important to us later on when we start plugging our values for voltages and currents into equations, and we have to do multiplications and we have to do divisions. Being able to manipulate and to very quickly go from polar to rectangular and from rectangular to polar is kind of important. So words of advice from somebody who's been through this before: spend a few minutes learning how to do that. You'll save yourself a world of trouble. But you're going to need to be able to manipulate, do a little bit of algebra with complex numbers. And remember, complex numbers can be expressed this way, with a real part and imaginary part. This is considered rectangular expression. This is considered polar expression. Okay? So that's the polar express right there. All right, so be able to do that. You're going to end up doing it quite a bit in here. Okay, so once again, the Phasor transform takes you from the time domain into the frequency domain. And that transformation is trivial. But once you're in the frequency domain, you can express numbers as in polar form or in rectangular form. And you need to be able to go very quickly between those two, all right, between polar and rectangular. You cannot be working in both domains at the same time. You cannot be working in the time domain and the frequency domain at the same time. It's either one or the other. It's probably going to not be understood well by most people until we dive in and do an example. So let's use phasors to do a little bit of math here. Let's say, and this is not a circuits problem, this is just in general. Let's say that I have one function here that is 20 cosine omega t minus 30 degrees. And I've got another function, y2, that is 40 cosine omega t plus 60 degrees. So I've got these two separate functions here. And here's what I want to do. I want to write some y function that is just y1 plus y2. Now, I want to express y, though, in the general form, where it has some amplitude multiplied by the cosine of omega t plus some phase angle. In other words, I want to take these two separate cosine functions that have different amplitudes and different phase angles, and I want to write their sum as just one cosine function with its own amplitude and its own phase angle. Now, this is possible. You can do this, but you can only do this if this omega and that omega are the same. If the omegas are different, then we don't know how to do this. We can't use our phasor mechanism in order to do this. We have to come up with some other way to do this. We can do that using phasors, but we could also do that using trig identities. I'm going to show you two ways to do this. The first way, we're going to use trig identities. The second way, we're going to use phasors. So let's go ahead and get started. And here comes the first method. We're going to use trig identities in order to do that. Now, here are the two identities that we're going to take advantage of. Cosine of alpha minus beta is equal to cosine alpha cosine beta plus the sine of alpha sine of beta. Okay, that's one trig identity that we're going to take advantage of. Here's the other trig identity. The cosine of alpha plus beta is the cosine of alpha cosine of beta minus sine alpha sine beta. So these two trig identities, you need to know those in order to accomplish writing all of this as one cosine function. All right, so our y1, which is 20 cosine omega t minus 30 degrees, could be written as 20 times cosine omega t cosine 30 degrees plus sine omega t sine 30 degrees. So here alpha is omega t and beta is 30, and we've just utilized that top trig identity there in order to rewrite this. We'll do the same thing with y2. y2 is 40 cosine omega t plus 60 degrees, and we're going to rewrite that as 40 times cosine omega t cosine 60 degrees minus sine omega t sine 60 degrees. Those are both square brackets. Okay, well, let's see. Since I can go through this and I can, you know that cosine of 30 and cosine of 60, sine of 60, and sine of 30, those are going to be numeric values. But when I add these two things together, y, which is y1 plus y2, is just going to be all of these things added together. So let's go ahead and distribute that 20 throughout and the 40 throughout and do the addition. And here's what I end up with. 20 cosine omega t cosine 30 degrees plus 20 sine omega t sine 30 degrees plus 40 cosine omega t cosine 60 degrees minus 40 cosine omega t, that's sine omega t sine 60 degrees. Okay, now let's take the things that we can and evaluate them. Let's see, the cosine of 30, that's going to be the square root of 3 over 2. The sine of 30, that's going to be a half. Cosine of 60, that's going to be a half as well. And then the sine of 60, that's going to be square root of 3 over 2 as well. Okay, take these values that we know for the sines and cosines that we can evaluate, multiply them by the numbers out front, and simplify it a little bit. And here's what you end up with. 37.32 cosine omega t minus 24.64 sine omega t. Okay, we're not there yet, but we had to go through that step in order to get to something like this, a single cosine, a single sine. And you notice the omegas are the same. Okay, and I've said it before, you would not be able to do this if the omegas were different. All right. Okay, now following through here, from this point forward, I'm going to use a trick. Here's the trick. Let's imagine a right triangle here. The right triangle has some angle theta right there, but the sides of this triangle are 37.32 and on this side 24.64. Those are the numbers right there, and that makes this one right here the square root of the sum of these two sides squared. And if you do that, that turns out that the hypotenuse here is going to be 44.72, like that. All right, so theta then is the inverse tangent of 24.64 divided by 37.32, and that turns out that theta is going to be something like 33.43 degrees. I'm just carrying it out to some arbitrary number of decimal places here. Okay, now why do I need this? Well, I need you to know this. Cosine of 33.43 degrees is going to equal the adjacent over the hypotenuse. So that's going to equal 37.32 divided by 44.72. And then the sine of 33.43 degrees is equal to, well, that's going to be opposite over hypotenuse, so 24.64 divided by 44.72. Keep these in mind, and now let's go back to our equation here. 44.72 times 37.32 divided by 44.72 times the cosine of omega t minus 24.64 divided by 44.72 sine omega t. All I did here is multiply and divide by 44.72. In other words, I multiplied by 1. I haven't really changed the equation any, but notice what I'm able to do here, 44.72. Now, this 37.32 over 44.72, that's this cosine. Cosine 33.43 degrees times the cosine omega t minus, well, what is this? 24.64 over 44.72, that's sine of 33.43 degrees times the sine of omega t. Okay. Now you might say, well, how did that happen? What did I do? Well, notice what we've got here. Cosine of an angle, cosine of a different angle, minus the sine of that angle, sine of the different angle. And now think back up here to this trig identity right here. I've got alpha and beta, cosine of those two angles minus the sine of those two angles. It's the same form right here. So working backwards, I can write this as 44.72 times the cosine of the sum of the two angles. And that could be omega t plus 33.43 degrees, like that. So I've got 44.72 times the cosine of omega t plus 33.43 degrees, and that is equal to my y1 plus y2. I have taken my y1 and y2 that I started with up here, and I have now successfully written them as one sinusoidal function, same omega, different phase angle, different amplitude. Now, you're probably wondering, that was a lot of trouble. Why are we doing this? I am doing this to illustrate how easy it is to do something like this using phasors. Okay, let's do the same sort of thing now using phasors. Okay, once again, we'll leave that right there. This is what we're after. We have our y1 and our y2. We want to write it in this general form. Well, take your y1 and convert it into phasor y1. Phasor y1, this is going to be 20 angle negative 30 degrees. Okay, the negative sign goes with the angle there. This one, phasor y2, is going to be 40 angle 60 degrees. Now what we want to do is we want to add these two things together. We want to do y1 plus y2. Okay, but in their current forms, we really cannot do that. We need to convert these into rectangular formats in order to be able to do that. So if we convert those into rectangular formats, then here's what it turns out to be. That's 17.32 minus J10. And then y2 turns out to be 20 plus J34.64. Now, how was I able to do that so quickly? Well, I have notes, but you should have been able to do it. Calculator, punch, a series of buttons, and very quickly jump to this. You can also kind of almost guess these signs here just to double check. This is 20 negative 30 degrees, so 20 is R, it's going to be negative 30 degrees, so it's going to be down here somewhere. That's the 20 negative 30 degrees to that point right there. So the X is going to be positive, but the Y is going to be negative. And that's how I'm able to, just a check to make sure that I'm in the right quadrant and I'm doing this sort of thing. For this one, it was 40 angle 60, so somewhere up in here. So that's going to have a positive X and a positive Y. Okay. All right, now that I've got them in this form, though, it's going to be real easy to add them. And you add complex numbers just by adding their real parts and their imaginary parts. So the real parts added together, this is going to be 37.32, and this is going to be plus J24.64. Okay, so we've added those two together. This is now phasor y1 plus phasor y2. And now that we've got it in this form, if I transform it back into rectangular, this is going to end up being 44.72 angle 33.43 degrees. And now that I've got it in this form, I can write, well, I do the inverse phasor transform. y1 plus y2 is 44.72 times the cosine of omega t plus 33.43 degrees. And there, I've just added the two things. And let's compare the answers. Yep, same answer. Obviously, this first way was a lot more trouble. This way was a lot easier, as long as you know how to convert between polar and rectangular and from rectangular to polar. And then you write your final answer. Remember, that doesn't change. The general form of the solution doesn't change either. It's going to be amplitude, same angular frequency, different phase angle. So really your job then in everything that we do from this point forward is going to be determining the amplitude, determining the phase angle, and you don't have to worry about that as long as it's the same, which it will be in every case that we're able to do. Otherwise, we can't solve the problem anyway. So it always has to be the same. Let's do another example real fast just so you can see this one more time. Let's say that I have y equals 100 cosine 300t plus 45 degrees plus 500 cosine 100t minus 60 degrees. And what I want to do is I want to write this as in the general form of some amplitude times the cosine of some, in other words, one sinusoidal function. All right, can I do this one? The answer is no, I cannot. And here's the reason why. 300 for the angular frequency, 100 for the angular frequency. So we couldn't do this problem. It's just beyond us at this point. We can't do it. So let's change the problem so that we can do it. We'll change that to a 3 right there. All right, now the omegas are the same. We have the ability to do this. That's going to be 300t plus something that goes right there. So we're after the amplitude, we're after the phase angle. That's what we want. Well, let's take our original function up here and transform it. Phasor y is going to be 100 angle 45 degrees plus 500 angle negative 60 degrees. Now I cannot add them when they're in polar form. I have to convert them into rectangular form to be able to add them. So with your calculator, you punch the buttons and tell me if you get this. 70.7 plus j 70.7. That's 145, so that kind of makes sense. This is the 0.707. This is what, square root of 2 over 2 number, all right? Plus, now you do the same thing for this one, and you end up with 250 minus j 433. I think that's 0.0. Okay, so this is 500 negative 60, so think about that. That's going to be down here in this quadrant. The x is going to be positive, the y is going to be negative. So, okay, that at least makes some sense like that. Now, add the real parts together, and I get 320.7. Add the imaginary parts together, and I get minus j 362.3. Okay, at this stage, I've done as much addition as I can. It's time to transform back into, do the inverse Phasor transform back into the time domain. But in order for me to be able to do that, I need to convert this from rectangular into polar. And when I do that, I end up with 483.85 angle negative 48.5 degrees. Okay, now it's real easy to do the inverse Phasor transform of this. 483.85 times the cosine of, remember omega is the same, omega is 300 up here, 300t minus 48.5 degrees. There, I have done what I set out to do. The amplitude is the 483.85. the phase angle is the negative 48.5 here. Okay. So once again, while all that we've done at this point is we have done some phasor transforms going from polar to rectangular sorts of things. I think we'll do one more, and then we'll let that be it. Let's see if I have one more. I may not have one more. Okay, yeah, I do have one more. Let's say y1 is 10 cosine 377t plus 14 degrees, and then y2 is 23 sine 377t minus 72 degrees. Okay. And once again, what I want to do is I want to write y1 plus y2, but I want it to be expressed as some amplitude times some sinusoidal function. And I could say that that's, now notice I've got a cosine here and a sine here. I need to pick one. I'm going to pick cosine. That's just because we've been doing that. Times 377t. The omegas will remain the same. Plus some phase angle, and I don't know if that's going to be positive or negative, but the phase angle is going to go right there. All right, well, in order to accomplish this, probably one of the first things you need to do is you need to convert either into sines and cosines. Since I said let's go all the way to cosines, then we need to convert this sine function here into a cosine function. If you don't know how to do that, once again, that's probably something you should be able to do. This turns out going to be 23 cosine 377t minus 162 degrees. Okay, so that's y2. Now I need to take my y2 and my y1. I need to convert those into the time domain, the frequency domain. So do the Phasor transform on them. Y1 is just going to be 10 angle 14 degrees. Phasor Y2 is going to be 23 angle negative 162 degrees, like that. Now let's add the two. Y1 plus Y2 is going to be 10 angle 14 degrees plus 23 angle negative 162 degrees. I can't add them together when they're in polar. I need to convert those to rectangular. A few strokes of your calculator. 9.70 plus J 2.42 minus 22 minus J 7.11. Add the real parts, you end up with minus 12.3. Add the imaginary parts, you end up with minus J 4.69. Okay. Now you need to convert from, let's pause for just a minute. This 1014, that tells me that that's going to be in the first quadrant, so I should have a positive x and a positive y. However, this one is minus 162. That places it over here somewhere. So there's my r, that's the 23, minus 162 degrees, means that I'm going to have a negative x and a negative y, and that's why these are both negatives here. Okay. When I add them together, I also end up with negatives, so I should end up with an angle that's down here somewhere in this, if I call this quadrant 1, 2, 3, and then this is 4 here. It's going to end up over here in the third quadrant somewhere. All right, let's go ahead and through the process. Once again, convert from rectangular into polar form, and you end up with 13.16 angle 200.87 degrees. This angle could also have been expressed as minus 159.13 degrees, or something close, so or that angle there. Now that I have that, I'm ready to convert back into the time domain, so y1 plus y2 is going to be 13.16 times the cosine of 377t plus 200.87 degrees, like that. Or I could write it as 13.16 times the cosine of 377t minus 159.13 degrees, like that. Either one of those would have been an acceptable answer. Okay, so what we've done so far is we've sort of played around with phasors. Next time we will see how you might utilize some of these phasor expressions in trying to find the sinusoidal steady state. That's for next time.